In the second class of chapter 4 of the course of basic geometry are presented definitions and properties of parallelograms and trapezoid quadrilateral parallelograms. In this first slide of this second class of chapter 4 of this course of basic geometry, it presents a figure 4.11 which shows a quadrilateral parallelogram formed by opposite sides parallel and of equal dimensions 2 to 2. That is, they are connected to 4 non-collinear points. This parallelogram quadrilateral has no right angles. Thus, in figure 4.11, the sides A, B, and CD have the same dimensions, and they are parallel to each other. The same is valid for the sides BC and the AD, which have the same dimensions and they are parallel one to each other. In the second slide is presented the calculation of the area of a quadrilateral parallelogram. The figure 4.12 shows a quadrilateral parallelogram whose area is given by the product of the dimension of the base BC by dimension of the rays h. The BC and ED bases have the same dimensions, and the CD and the AB sides are parallel and have the same dimensions. So the triangles BEA and CFD are the same, and the straight line segments AE and CF are equal. The area of the BFGE rectangle is given by the dimension of the base BF multiplied by the dimension of H. The area of the parallelogram quadrilateral BCGA is equal to the area of the rectangle BFGE minus the area of the two triangles BEA and CFD. The area of the triangles are equal to the dimension of the straight line segment AE multiplied by the dimension of the straight line segment of height h divided by 2. Therefore, the total area of the two triangles is equal to the dimension of the straight line segment AE multiplied by the height h. Thus, the area of the parallelogram is the area of the rectangle minus the area of the two triangles. Thus, the area of the parallelogram is given by the product of the dimension of the straight line segment BF multiplied by the straight line segment dimension of the height minus the product of the dimension of the straight line segment CF multiplied by the dimension of the segment of the straight line of height h. By the dimension of the straight line segment BF minus the dimension of the straight line segment CF is equal to the dimension of the straight line segment BC, which is the base of the parallelogram. Thus, the area of the parallelogram is given by the dimension of the straight line segment BC of the parallelogram multiplied by the dimension of the straight line segment of height h. This slide presents a definition of a rhomboid parallelogram. This type of a parallelogram has dimension of all sides equal. A parallelogram is said to be rhomboid when the dimension of all sides are equal, but the angles are not right angles. These diagonals are also the bisector of the angles. The intersections of the diagonals is the incenter of the rhomboid parallelogram. The incenter is the center of the circumference to the rhomboid parallelogram that touch all sides. The diagonal that connects the vertices A and C cuts the bisector of the angle at the vertex B in incenter, forming two triangles with two equal sides, and with the vertices A and C connected by a single segment of straight line AC. So it's possible to draw a circumference inscribed in the rhomboid parallelogram that touches the four sides. This slide shows the calculation of the area of the rhomboid parallelogram. This type of a parallelogram is a special case of parallelogram, so its area is calculated using the same formula that defines the area of a parallelogram that is equal to the product of the dimension of the straight line segment of the base BC by dimension of a straight line segment of rate h, as shown in figure 4.14. In the second half of the slide, it is presented a definition of a quadrilateral trapezoid. This type of quadrilateral is shown in figure 4.15. The trapezoid quadrilateral has two parallel sides, called the base sides, and two non-parallel sides, called lateral sides. The bases AB and CD are parallel. The interior angles of vertices B and D are supplementary, that is, they add up 180 degrees. The sum is true for the interior angles of vertices A and C. This slide shows the definition of the Scalene trapezoid quadrilateral shown in figure 4.16. A quadrilateral scalene trapezoid is said to be scalene when the four sides have different dimensions, and the two sides called bases AB and CD are parallel. The second half of this slide shows a rectangular trapezoid quadrilateral. A quadrilateral trapezoid is said to be rectangular when one of its sides is perpendicular to its base. That is, this type of quadrilateral has two interior angles of the right type. This last slide of this second class of chapter 4 of the course of basic geometry presents a definition of isosceles trapezoid quadrilateral. A quadrilateral trapezoid is said to be an isosceles trapezoid quadrilateral when the two non-parallel sides have the same dimension, as shown in figure 4.18. In this case, the vertices of the interior angle A and B are equal. The same is true for the angles of vertices C and D.